All right, welcome everybody. This is the MS in Architecture, Computational Technologies. I am Pablo Lorenzo Iroa. I'm the director of the program. And today we have the pleasure of having our innovation keynote lecturer, Kaicong Wu, who is going to be discussing robotic assembly, a generative architectural design strategy. The MS in Architecture Computational Technology is a new program that at the New York Institute of Technology School of Architecture and Design. And we are starting with Kaicong Wu this summer lecture series that is going to be discussing the relationship between information processing and the physics that become active in robotic fabrication. So the lecture series is entitled Inform Actualizations from AI to Physical Computation. And the lecture series ends up discussing research frame by invited guest speakers and focuses on expanding the relationship between science, technology, culture through innovation, algorithms, simulations, AI, robotics, and materials. The lecture series ends up discussing alternative means to understand the dialectics between the ideal digital and the physical digital. And we claim that we're trying to activate what we call an architecture of information, which happens exactly at the moment in which the relation between the two realms or the two media or the two mediums actually go back and forth in terms of information processes. Kaicong Wu is an assistant professor at the University of Hong Kong, probably you know Hong Kong University. And his lecture today is entitled Robotic Assembly, a Generative Architectural Design Strategy. The description of the lecture is as follows. Architectural assembly has been neglected research topic within the field of computational design. Instead, manual assembly and passive fabrication processes directed by top-down controlling geometric models have attract more attentions. Such design to production model is problematic because it is difficult for designers to overcome the constraints of their empirical knowledge. An extensive amount of resources can be wasted when architectural components are manually assembled. However, what has yet to be determined is whether the applications of advanced assembly machines, especially architectural robots, can reduce resource use and create new design principles. So the question is, can robotic assembly become a generative strategy to discover architectural forms? Kaicong Wu is an architect, designer, and researcher. He received a PhD in architecture from Princeton University in 2019. He also holds a master's of architecture from University of Pennsylvania and a Bachelor of Architecture from Shanghai Jiao Tong University. His current research focuses on architectural design and design technology, especially generative design strategies informed by computation, deep learning, material sensing, and robotic assembly. Welcome, Kaicong, and thank you for joining us.
Thank you, Pablo. Thank you so much for the kind introduction and inviting me here today. So hello, everyone. My name is Kaicong. The title that I named the lecture today, it's called the Robotic Assembly, a Generative Architectural Design Strategy. So this is something that I have been working on kind of for a while already. So which started from my PhD dissertation, right? So the general idea, I think, is to consider when we have these advanced machines, I don't consider the decision making, it's only coming from the human, right? So I think my intention is to let these intelligent and more advanced machines to actually step into the design decision-making process. So I will try to kind of like explain my motivation by quickly introducing something before I connected with the robotic fabrication, robotic assembly, right? Because I'm always kind of like keep myself like updated with all these new design technologies, right? Either computing or the fabrication tools. But I think at the same time, I was also thinking about the role or their impact to our design process, right? So I think in my mind, like if we consider the pure computation can help us to model different complex design architectural forms. I would consider they are in the contribution of modeling, right? So either we write a program to run a pattern, or we kind of like parametrically model certain relationships and let them change. I think I consider they are all helping us doing the modeling, right? And I think that the current development, which kind of like inspired, kind of further pushed by these new either AI or robotic fabrications, I do see that these are stepping into the design automation, which can pretty much help us to automate the design from the conceptual stage to the production stage, right? But I think in the future, especially when we have more access to the deep learning artificial neural networks, I can foresee that I think the machines are becoming more and more intelligent, and I think that they will not just become like a receiver which produce the design, but can actually contribute to actually find, discover the design. So I think kind of like in my overall projection in the future, there is a certain of autonomous design will happen in the future. So following that kind of clue, I would just explain like what actually triggers me to step into using industrial robotics to produce architectural forms, right? So as you see in this kind of video, this is something I tried many years ago. So it's like really in my early design career, I started with writing these algorithms and to sort of finding this emerged order, right, from these kind of irregular forms in the beginning, right? So although they're loosely positioned, but you can see how they can generate this order by trying different rules, right? So it's really rule-based design, but also I found like there is this kind of like emerged pattern, which if you do that manually, it's, I'm not saying you can't find that, but I think it's rather difficult that if you organize all these different components together. And I think why I try these multiple components is because I think for architectural forms, we can't expect anything to always be fully produced as a holistic geometry, right? So it always has to be divided into the parts. So I think when we try these very abstract components, we find the order, but we can also start to, using digital tools to kind of like materialize them, right? So give them massing, give them thickness, and then they will not just be like abstract pattern anymore, but they can wrap around as a real building skin, right? So this is something like I kind of like studied, especially when I started with Roland Snooks and Cecil Barmont at UPenn, right? So and we sort of like really fascinated by these kind of emerged algorithms, and then try to use this self-organization process to generate these building skin, building envelopes, and then they can, not just stay on the 2D, but they can wrap around. You can imagine almost any three-dimensional form. They can be flattened as a 2D kind of like surface, right? You can just wrap it around to go back to the 3D. So the purest emerged order can always still be there, right? So this is something kind of like straightforward to read. But I think for me, of course, it seems like really difficult if we consider this to become something from the digital space translated into the physical space, right? And I found like before I realized to use robotics to help us, I do find it's really struggling for me to think about how to materialize these things. So that kind of like drove me to think further, if there is the new kind of engagement of these new advanced fabrication tools, maybe something we programmed in the digital space, they can easily be translated into the physical world, right? So, but I found like through such kind of translation, if we imagine there's certain building envelopes, building skin that are divided into the components, but then we have to find a way to fabricate them. And I think a lot of time, like when different researchers, pioneers step into the robotic fabrication field, of course, making it's kind of like naturally very attractive to architectural designer, right? So of course, but I think we have to think about how to put them together. So I think for me, instead of thinking too much about how to make, I mean, I'll of course think about how to make these components, but I think to me, the more interesting part is how we put them together. And I see a lot of time, like even with the advanced fabrication machines, even with industrial robotic arms, I see the components, if we construct into building forms, they are still manually positioned at a lot of times. So I found that like that part is kind of like problematic to me, because in the end, I see that the contribution from the digital fabrication part, they are still following this very linear kind of production line, right? So from the conceptual model, and then start to do the different kind of fabrication and start to use more and more labor to assemble them back into the form that we modeled in the first place, right? And then it's actually very difficult to challenge our empirical knowledge, because everything's still, I mean, of course, there are still feedback, of course, right? You have to realize the limitation and such, but I think at a certain point, I found that like the feedback loop is just so long, right? So I know, and I think it's important to shorter that and to really light the digital and the robotic fabrication technologies to challenge our conceptualization process. So I think so once these kind of, especially these later steps through the not just about the making, but also the assembly. Once they are fully automated, I think that there is the chance to actually going back to push us to think about maybe there are potentially unknown kind of design principles that we cannot use. I mean, we have to use new knowledge in order to find the kind of discover the new potentials, because otherwise it's still going to be quite a similar design process, but of course we can increase the complexity. But I think just increase the complexity alone may not be enough, right? So that's why I found like for me, I kind of like set up in the very beginning when I worked with the industrial robotics, I kind of like define my goal is to think about how to use them to assemble components. So that's why I think the assembly is a really kind of like for me fascinating area. And I found that they are, this area is a lot of them quite easily to be ignored, because we are, yeah, as I said, naturally interested by these making problems. But then if you think about how to put them together, there are actually more potentials and more way to challenge ourselves. So I will quickly introduce kind of like 3 projects that I did before, which start from something very simple in the beginning, because when I start to think about, okay, how I assemble things, the first thing coming to my mind, it's almost like a puzzle, right? So you can imagine the puzzle is almost like the basic assembly problem. And I do see that the freeform or any kind of like today's building envelopes, they're not going to be the standardized geometries anymore, right? So we have to find an intelligent way of making them, but also find an intelligent way of assembling them as well. So, but in the beginning, I still cannot get rid of my old thinking, so I start also by using a guiding geometry, divided into these components, right? And then start to, laser cut them one by one and start to glue them. This is kind of like everyone will do this. But then I realized it's actually a very tedious process, and I kind of like need to use a lot of guidance to find the index of each component and then either cluster them, right? So either to kind of like simplify the geometries, all these optimization, all kind of like a sequence kind of computing, right? So we can all do that. And then I pass these irregular geometries to the robotic arm. So you can see the robotic arm can hold piece by piece of the materials and then to cut them into the different shapes, right? So this is actually quite straightforward. And I think, yes, the robotic arm is definitely helping, but then it's in another way, it's not making such new difference, right? So if I don't have this robotic arm, it's just time, right? And the labor, I can still make that. So that's why I found that it's not enough. And I also noticed a very at that moment, I thought it's a it was a small problem. As you see, I have to place a much bigger panel than the computed component in order to make a successful cut, because if it's too small, it's very easily to just like halfway cut the components. But then all these leftover, materials, they're just gonna be gone, right? So, and I never got a chance to really reuse them again. But on the other hand, I noticed a very kind of like a simple animal, which is this caddisfly larva. As you see, it doesn't have the accessibility of cutting any of these pieces, right? And this is the artist using this animal to actually make jewelry. And then you will see the animal just picking these kind of like fragments, and by reading how they fit into each other, build up its cocoon. So I found that even like this small insect has such kind of amazing feedback intelligence in it, right? And I kind of like using a very manual, brute force way of producing all the components. So I sort of like, what if I do this way? And I can imagine like I can take one of the components, and then I just kind of like approximating the shape and then cut it and then assemble it, right? That's of course one way, but then it's still the question, of course, these leftover pieces are just still cannot be reused precisely. So then I start to think, okay, what if I gave the robotic arm an eye, right? So I start to position in this Kinect sensor, for those of you know this, it's just a 3D scanner, right? So it's shooting out the linear lines, and then you will actually detect the shape of any component that not component, any material piece that you positioned in front of the camera, right? So using this depth camera method, and also I start to link in the entire kind of like a detection, but also picking up the components, and also directly after the cutting into the assemble the position as one continuous process. So once I fully realized this automatic design to kind of like a computing to production process, I can randomly position any components on the table. I don't have to worry about their orientations. And then also, another amazing thing is I don't have to worry about how many like leftover pieces I have in the end, because all these ones can also be again tracked by the sensor. So before I don't have this accessibility, I have to pre-cut everything, right? So everything is prefabrication. But now, instead of using kind of approximated way of doing that, I can actually use the point cloud scanned by the sensor to actually detect the shape of any component or to be cut material piece, right? So even though there can be irregular, but I can compute which position it fits the best into the current kind of like a shell, kind of edge of the ongoing shell structure, right? So I can always kind of find the best fitting moment and use that position to actually guide the assemble of the material piece, but to decide also a very minimum cut. So as you see, I can only cut a little piece, and then to either perfectly assemble it or can leave certain openings. Depends on the threshold or how rigorously I want to fit into this shell, right? So then there are different ways of sensing. And I realized I don't have to design any components like before anymore, right? So before it was like you have a material piece and you sort of like imagine there's a component embedded into it and you cut the unwanted parts. But actually you don't have to do that anymore because it's exactly the shape that detected. It's almost like a found material piece. You can directly use the shape to regenerate all the components, right? So, and then as I said, we can set up like the threshold to decide, how well we want them to tightly fit together. If we really want them without any openings, of course, the trade-off is the waste, right? So, but of course, if we give it a certain leeway, right? So make the allowance of these openings, and then you will find like you can do a very minimum cuts, which reduce the previous amount of material waste to very minimum. But I think to me, in this project, the sustainability is not the key. It's not about like how much material waste I can receive, but I found out like this evaluation of using the material waste as evaluation, it actually regenerates new forms, which if you don't use this criteria, you will actually not do this way. And I, as a designer, I'm not the one that fully make the decisions. There are a level of uncertainty that are in the system. So I think that it's the kind of like the starting point I found out, okay, the robotic assembly will not be just like a receiver, right? So it should be able to step in further and further. But then the question, of course, it's the panel at that moment I build up this shell structure is still rather a very simple problem, right? And then if we think about what about 3D, those are just 2D panels. If you think about how you put the things, three-dimensional objects together, let them fit each other, it's actually very harder, much harder problem. So then if we just program the fitting logic, it's not going to work, right? Obviously. So then I start to think about what if I can start to light the intelligent technologies, right? Like artificial neural networks to handle such complexity. So, and I do see such intelligence actually have, I mean, it's among every, human designer, right? So we as a human, we naturally, through practice, you can see these artists are built up by their own hands of these natural wood logs without really, processing the wood logs into standardized materials. They don't have to, right? So you can just through intuition, through practice, you can make, amazing structure from there. So I think as such intelligence, there's another level of higher than just reading the geometric features, right? There is the decision making of the configuration. So that triggers me to think about, okay, so what if I can use that as another driver, and then it will not just save material waste, right? So, but at the same time, of course, we can actually entirely bypass this kind of traditional material industrialization process, right? We don't have to send the natural material, the raw materials into the factory anymore. We can just allow the raw materials to be constructed directly on site. But of course, we all know this very famous project done by the DRL, right? So the wood chipborne project is using all these 3D scanned kind of tree branches, and then to also use evolutionary computing to find their kind of optimized connections to build up these truss structures. And I think it's really a beautiful project, but I think my question, or kind of like my critique, is about, if you think about the process, right? It's actually a lot of brute force scanning steps in the beginning, right? You have to collect all the trees, and then to kind of like pre-select them, and then to also scan every geometry, and then collect this big kind of material library. Then you start your design. So, and then at this design part, it's still actually quite using our own knowledge. So I think I want to think about like, what if I redo this kind of process? What if the design can happen much earlier, right? And so I sort of start to imagine a new setup. And I do think at this moment, there should be another decision maker, which is not just me, but they should come from an artificial kind of brain, which is also making decisions, not about like how the material geometries are fitting into each other, but also to read the configuration to find the most meaningful ones. And then I kind of also was inspired by this kind of robotic pickings research, right? And I think it's very robust, but fascinating part is when the robotic arm is trained to pick up these daily objects, there's no rule, right? There's no program. And it's really through trial and error. And only some gesture will make the picking successful, and some gestures actually will fail, right? But then through the training, through the learning, in the end, the robotic can be self-driven by a camera only, right? Without any additional information to successfully pick up any new objects that are previously not inside of the training data set. So I think maybe I should use the same strategy of design a structure. Right? We can imagine like I only set up the general environment. For example, the goal of the structure is just connecting the two supports, but then I don't provide any guiding geometries. And then maybe through trial and error, we can collect a certain meaningful configurations, and then like the artificial neural networks to learn the complexity, and then to reach kind of drive self-drive the robotic arm to assemble new wood log materials. Right? So that will be the major setup. So the major difference compared with, let's say, the AA project is right now, as you see, I scanned every single log. But then right after the scanning, we know the geometries. And then immediately I will start to compute their potential assembly positions. And because we don't know where to put it, the best shot is just try it randomly, right? So in this process, I also use evolutionary computing, but then there are multiple evaluations that we have to put into the calculation to avoid collision to the existing structure, for example, but also avoid colliding into the basement, right? But we also want to realize higher and higher structures, but also connected the two parts as the objective, right? So all these evaluations criteria will be all considered into the loop. But also it's not just computing the final position, but actually it's computing all these middle steps as well. So make sure that during the process of the robotic arm, position the log, there will be a clear toolpath and without collision as well. So I think it's almost like giving the robotic arm a very direct task. It's like you have a log in your hand and then to position it into a structure without colliding, but also the structure has to be meaningful. But how to let the structure to be meaningful? What I did is I set up these cameras. So during this trial and error process, we can collect all these database. And basically, this part is a little bit of manual work. I have to manually kind of like label which log or which certain kind of steps are doing great, which are not, which is quite based on a very simple evaluation criteria. I'm just reading whether they can build up this three-dimensional triangulation, right? So as the way of reinforce the structure. So if there's anything too random, I would just give it a minus kind of label, right? So if otherwise, I would just consider that's a positive gesture, right? So so yeah, during the entire trial and error assembly process, we can actually let all the cameras to give us a very large database of every single steps that the camera sees the kind of the environment and what are the kind of like the angles of the skeleton of the robotic arm, right? So it's like really building up this hand-eye coordination database. So we can imagine any decisions that we make during a production, there is this kind of kind of hand-eye coordination, right? So there's coordination, and I do see that coordination is part of the design, kind of like intelligence, the intelligence of achieving the design objective, right? So then after I collect all these images together with the 3D scans, wood log geometries, we can all pass through the a very wide artificial neural network and to let it map into the 6 joints of the robotic arm, right? So the hypothesis is whenever the camera capture a kind of image, which is recording what the robotic is making at that moment, it should make a decision how to drive the 6 joints to move to the next step, right? So the entire design, whether it's a geometry configuration, whether it's a two-pass planning, can be all simplified into the current status of the image and then the decision making for the next small step, right? So then after the learning, we can pretty much run this to let it control, let this artificial neural network to control the robotic arm. So as you see, it's it's actually making giving the robotic arm a quite hard time. There is this kind of like a not sure moment, but also increased the kind of like the difficulty as you see these branched Wu logs are not included in the data base for training. So there are new data, and I think in the end it still finds a way of reading the geometric features and also has this kind of experience of avoiding the collision and such. So, but at this moment, I think to me, the meaning of doing this is I do see that there is the potential of designing these natural wood log structures without the necessity of defining what is the target geometry, right, by ourselves. We can, if we can set up the learning perfectly, if we can set up the criteria perfectly, we can actually achieve a meaningful structure by using robotic arm to repeat certain kind of like example gestures, but also not just repeating, but also discovering potential also other meaningful assembling kind of gestures. Which, if we do that, if you test that manually, of course, we can still do that. But I think that the key is to let this process reflect the way how we think about the decision making during conceptualization and the production. So, but of course, the limitations right now, as you see, I only use one robotic arm all the time. And then I start to think about what if there is another level of complexity. So by using multiple robotic arms, and then I start to research about the collaborating potentials of using robotic assembly. So, so this is mainly the experiment setup. There are two robotic arms. They will kind of sequentially produce these compression-only arch structures. And so, I mean, it's, I mean, as a, to build up an arch form of, and then without using too many scaffolding components, it's actually a very, old kind of problem, So even like in the medieval kind of like age, people are using these stones to kind of like always compression the end of the arch branch, right? And then to maintain the equilibrium of the arch structures in order to let the structure grow without creating huge scaffolding in the middle. So and also like the form funding as another kind of very unique but also well-studied method. It can always produce these very robust compression-only arch forms, but there's no free lunch, right? So the for those of working on this already, that form funding, the kind of most difficult part is actually the scaffolding, because you need these very precise CNC milled geometries to support each single component, because they have to follow these compression-only arch geometric lock profiles, right? So any small differences will make them not working so well. So to avoid the bending forces, right? So, but that kind of scaffolding, as you see in this project, is quite consuming. Not just the labor time, but also if you think about your design to production, maybe like 80% of the time you are making the something that is not kept in the end. So I was thinking, what if the robotic arm can step into this? In the beginning, it was just providing a temporary scaffolding system. But as you see, if we program the sequential positions of the two robotic arm, we can build a single compression-only arch from one end to the other end without using any other supports in the middle. Right? So this is kind of like a very straightforward way of doing that. And we can actually combine both the cutting of these of these compression-only components, and then also the positioning of them. Right? So through the sequentially changing of the positions of the two arms, we will see this branch will grow from one end to the other. But then the problem is every single branch, even though it's a very simple geometry, very simple structure, I need two robotic arms to kind of like assemble it. And then, at that moment at least, we only had 2 robotic arms in the lab. And then that means I can only always design a single branch arch, right? Which is, if you think about the design potentials, is almost nothing, right? So obviously I want to do more. So I was thinking, what if I want to do multiple branch structures? And I immediately will realize it's actually using more and more robotic arm in order to make that. And then, that's gonna become something quite tricky because, of course, we can keep investing more money to buy more robotic arms. But then, it's actually, I was thinking we are not using the assembly to its extreme, sort of saying, right? So then I start to imagine, what if we change the end effector, right? So make the tooling change. And I start to imagine, start to conceptualize, but also customize these end effectors, which I included these caterpillar tracks. So, and also these kind of linear actuators to control precisely the angle. You can imagine what the function of this new end effector is. It will not just holding the components, but by holding it, by providing the compression force, it's also kind of like moving to the next position. So the caterpillar tracks will make sure there's always compression force, but it can also synchronize with the movement of the robotic arm to the next position. And then another problem we need to solve is, because of these new multi-branched structures, there is the keystone problem, right? The keystone is actually very complex because of these new connections. And as you see, when we cut that, it's actually gonna exhaust kind of the degree of freedom of the axis for the one robotic arm. And as you see, I have to switch to the other arm to cut the rest of the piece. So this is kind of like a more detailed problem. But once I figure out this keystone and the previous synchronization of the positioning, as you can see, we can keep increasing the complexity of the structure. So almost like you can pretty much design multiple branched structures as long as the highest valence of the joint is 3, right? So you can use 2 robotic arms to keep increasing the complexity of the form. So, but of course, there is some other tricks I have to figure out, like the sequence, because if you entirely follow the structural kind of growing line, at a certain level, the structure is just gonna be too heavy, and you have to find a way to always let the robotic arm to go to the kind of easier position to reduce the load to the robotic arm, right? So because I mean, these arms, they are very precise, but they're not like strong to something that you can hold up, for whatever weight you want, right? So the position also definitely matters. And I do see that by just using this setup, it can totally change the entire, concentration that we spend, right? So rather than like kind of consuming a lot of materials, producing this scaffolding, and they probably only be used one time. And but on the other hand, I mean, this robotic arm with the linear tracks, they can be considered as a new investment, but then they can be reused all the time, right? So it's also another way of redirecting our resource and to put us to not like consuming our energy into the production of, as I said, something that we don't keep in the end, right? So we can put our more energy into the design of the geometry, right? So once we figure out the entire automatic assemble and fabrication process. And then another amazing thing is, because these robotic arms will actually hold the kind of like to be constructed structure temporarily, we can actually change the design. Even though like some parts is already built, we can still keep changing the rest of the geometries, which we don't have this freedom if we traditionally use scaffolding. Once the scaffolding is produced, you're done, right? So the design cannot be changed. But now we don't have to rebuild the existing parts, but still the new additional parts can be redesigned. So I think that's sort of like what I see by just using 2 arms, where we're using the collaborations. As you see, there are another degree of kind of freedom we can find through the design to production. So as I mentioned in the very beginning, right? So in the digital computing part, I can see they are helping us modeling. But once we step into the robotic fabrication, especially if we kind of like put it into the assembly into the loop, the design to production can be fully automated. So in that case, I would say it's design automation, right? Because at that moment, we don't have to worry about the production, right? So we only focus on the design. But I think with the intelligence and more of these kind of complex but also intelligent machines, but of course with the help of different types of sensors, sensory technologies, we can imagine that in the future, the decision making will actually coming from more to the machine setups, and they can actually help us to make decisions, which we traditionally, if you do them, which we traditionally, I think, were usually manually done. But once we use this system, they can be totally manipulated by machines. But then it doesn't mean that we don't have anything else to do, right? But then we actually can think more about what is the design space, right? Are we using the design space kind of like fully enough, right? Are we using the correct design criteria or not? So that will make all this new kind of thinking into the kind of like think of the potential contribution of these machines. Right? So yeah, hopefully I can sort of like you see, my argument is in the future, these machines will not just become producer only, right? They can actually help us, at least, I would not say that they are designers, but they actually can discover forms if we use them and to try to use them also challenge our existing knowledge, right? So yeah. So as a conclusion, that's kind of like my general argument and what I'm currently also keep trying to do further. So yeah, so hopefully this can kind of like can trigger some discussion. So please, yeah, thank you.
Yes, thank you so much. Before I keep calling you Kaicong, so the pronunciation of your name is Kaicong?
Yeah, I mean, it's I mean, from in Chinese it's called Kaicong, but the C is more like a TS, so it's yeah, so it's Kaicong.
Like when we were well, it's like internal to our school, but we were calling you Kaicong, so I apologize.
No. I mean, it's not you. I mean, whenever I go to foreign countries, I'm always become Kaicong, so it's still me. Don't worry.
Okay, so thank you so much for such an insightful presentation, and also for the what I appreciate is the originality. You're like the type of person that I like, because you like getting in trouble with things. You don't like to in a way to follow. You're not following the typical problems of fabrication in relationship to robotics. And therefore, you're kind of like trying to develop an area that I truly call this transdisciplinarity, because you're expanding architecture in relationship to identifying areas that had not been explored, and therefore you're like redrawing the map of what architecture is by expanding the possibilities of the territory. And I really appreciate the architectonics that your investigation has in relationship to the history of the relation between architecture and technology in relationship to assembly, because and I appreciate a lot what you mentioned in relationship to Brunelleschi, because I study problems such as those. And I'm particularly interested in the feedback, right? Like, as you said, because you're actually very precise about identifying that the problem of knowledge, right? Like for instance, you were like really identifying the problem of Brunelleschi in terms of not only devising the dome, but actually the means of construction as a knowledge-based problem in terms of the process of construction, which I also have been researching on a lot, and also in relationship to Gaudí, right? So your lecture is actually very welcome in terms of what we're doing now, because we have been working with Gaudí last semester with our students in relationship to clay, 3D printing, and problems of deposition in relationship to activating catenaries and so on. So what to me, one of the most interesting things that you mentioned, which makes your work a little bit more interesting than the typical one, is what you denominate in terms of knowledge, because you understand the problem of bias in terms of architecture going back to a safe territory of knowledge, and you're trying to discover what are the new relationships that we can find in terms of robotic fabrication, in terms of expanding that knowledge, pushing forward. But at the same time, you're actually thinking in terms of assembly, both in relationship to what the tool allows you to do, in this case, a robotic arm that you are also critical of. That's what I also like. I actually, in Acadia, I've been like always kind of like a weird guy, because I'm always critical of the cycle of replacement, right? And the kind of naive, if you want, positivist approach to technology, that every time we have a new tool, everything is supposed to change, but we're not really critical of that new tool. And you are identifying the ranges of possibilities because you need them, right, in terms of a robotic arm, and you question the robotic arm in terms of the assembly. So the other interesting thing that you mentioned in terms of the knowledge, how do you see the expansion of knowledge in relationship to because you're also, some of the things that we're working with, we're actually trying to, we based this program in terms of 3D scanning on the problem of machine vision, right? We did an entire semester working with point clouds. And so I just wanted to ask you, like in terms of critical terms, right? Like you're working with 3D scanning on the one hand, you're working with the robotic 3D printing, and then you do a lot of things that have to expand the robotic 3D printing, right? So I just wonder if you could think about the possibility of leaving behind the robotic arm, or like what would be, because you're developing little machines that they are in relationship to the robotic arm, but because you are aware that the robotic arm is not enough, right? You have it on tracks. Actually, I like a lot. I studied at Princeton, so I like a lot how you're using the space of the new Fab Lab, which is actually fantastic.
It was not there when you were there. So
yeah, it was not there, and we were, and but I know the trip. In winter, from the School of Architecture, I had to go all the way there with the snow.
Yes.
But I was thinking the relationship between the space, because you're also, in a way, I don't know, maybe it's not on purpose, but you are trying to engage with the space where these things move, right? And I paid attention to that. And there were some beams that you were not using, but I'm sure that you were thinking about, like, how these robots are moving, how can I engage more axes and so on. So what do you think your work would actually move? Can your work move beyond the robotic arm, or how you're thinking assembly, like even in theoretical terms, like even if you didn't resolve it yet?
Yeah, thanks. I think that this is exactly kind of a question I keep thinking for a long time, and I have to say it's not easy. It's not that easy. Yeah. So first of all, I do see there are many different levels of using, let's say, industrial robotic arms. I see sometimes people will consider there are another new CNC machine, right? It could be explained like that. And it's just like compared with milling 3D printing, it has 6-degree freedom, right? So it's higher degree freedom of CNC machine. It could be imagined like that. And then you program, and then you have some more complex things produced. So this is one level, right? So obviously. And then another level I see more and more, it's there is the feedback. So because this robotic system is also open source, right? So it's sort of like it's open hardware. So you can connect with other tools, which you can embed into the sensing feedback. If you let the computer vision to drive this fabrication process, there are many steps you will make very differently, right? Some geometries, like I mentioned, you don't have to design them, but just to design the feedback loop, you can actually achieve something that is actually not there. There's no digital model with that, right? So I would say that's kind of like a next level. But then I would say it's still not enough because I mean, the reason why we call it robotic arm, why we call it robotic, I think that there is this kind of mimicry, right, embedded into the system, and we sort of like mimicking us, right? It's a hand, and it's sort of like making things like what we use our hands. So what I kind of like ultimate goal, which is I don't know whether I can really achieve some good results. It's to really let this system not just mimicking us, right, as a human being, how to manipulate materials, but to try to understand what's actually the intelligence, right, of design. Because it's something, if we keep talking about it, we can keep talking about for a week, but with no answer, right? But then through these experiments, I found if you consider the model of design process wrong, you will end up with something entirely wrong. So I think that's actually, for me, it's a helpful way of using these intelligent machines to model the design process. But of course, making it's only part of the design process. So that's why I would say, especially after these kind of woodlock projects, I already realized, the reason why we see human beings, when we see craftsmen make these woodlock joineries, it's not just about geometry and how they fit each other. There's also another higher level information, right? Because they are considering structures, they are considering even program already, right? So every single tectonic system, there's actually the symbolic meaning behind. So it's not really, it's much more than material manipulation. So although I finished, I already challenged myself during the half of the project. I know this is not enough, right? So we actually think more complex than that. And I think, so that's why I think for me, to actually go beyond robotic system in terms of the setup, the environment, I think that's the goal. So I think, but I think to go beyond that, we can't use anything only inside the space, right? So sometimes, for example, like what I did is a setup environment, which means from the computer vision, the robotic fabrication, the entire system only use all the information within this box, for example, right? But actually, there are out of the box information influencing the design. If we think about it as a human being, right? So the knowledge, the experience, the memory, they all make our decisions. So I think those are the parts I see to, at least from my point of view, to see how we can push to really like these tools to produce something that is very different from the past, which I think to me, the difference has two meaning. One is to entirely make new things, right? Be creative. And I think that's the alternate goal, not just for me, I think for every single architectural designer, we want to be different, right? And the other thing is, as I said, I want to use this as a way of modeling really to think about what is the intelligent process that we have been, going on in our mind when we draw things, when we make things, when we kind of like model geometries, right? There must be certain higher level. And I can't see that if I keep doing material tests, I can realize that, no, that's definitely not possible. Yeah.
So, so no, I like a lot what you're saying, because, when Gramasio Kohler started working with a robotic arm doing the brick walls, right? Yeah. I was in Argentina. Actually, I was already in Princeton. I did Princeton in 2001. But I was coming from Argentina. We were already building Eladio Viestes walls. I happened to work with, we had an architecture firm that we were looking at curvature with brick walls. And we were looking at parametric design in relationship to gaps and opening, and we developed actually beautiful buildings working with that. That then they became, actually some of them were published a lot. And I was seeing these guys in Switzerland, you know, and forgive me, I'm not politically correct, right? But I'm from Latin America, right? And you know, everything is about you know, cheap labor and expensive materials, right? And you work with the workers because they are thinking while they're working. It's not that they are giving an instruction and then they just do it. They're actually,
there's a dialogue. There's a dialogue.
I enjoyed a lot working with workers that they were happy because they were understanding what we're trying to do, and they say, look at this, and they were actually agents in changing the design. But and then when I saw Gramasio Kohler doing it with a robot, I said, oh my God, this is totally wrong, right? And I wrote about it actually. I was very open about that criticism because I was working with robotics, and I was saying, okay, the robotic arm is entirely wrong, right? Because of exactly what you said. Actually, I put it in terms of symbolic form relative to deep structure.
Okay. There we go.
I actually studied at Princeton with Hal Foster, and he.
Well, from the art history department, yeah.
Yes, exactly, and I work a lot the problem of deep structure in terms of symbolic form, and the problem of the anthropomorphic mimicking. You call it mimicking. To me, is even more problematic than mimicking. It's actually sedimenting the entire problem of computation. First, by imitating the brain, and second, imitating the body, right? So in AI, we have that problem already. We have the problem that I think that if we keep trying to do AI by imitating the brain, I mean, it's a lot of people already said that is a problem, right? That we need to focus on AI, thinking about the artificiality of it in order to actually think that it's a different type of intelligence, that is a mathematical-based intelligence that is doesn't need to imitate the brain. And I think the same happens with robotics arms, right? And I'm trying to figure out, but at the same time, we need to work with a robotic arm. Like, so it's a little bit of what because you have to, you know, yes, we have the robotic arm. We need to use it at the same time where you are expanding it from outside, from the space and so on. I'm trying to actually deconstruct the robots in relationship to what they are able to activate. But you also mentioned the feedback, right? I think that we're all aware of the problem of the feedback loop in terms of not only feedback at the level of the AI machine learning, right? But feedback in terms of the relation between abstract computational thinking in relationship to what actually happened at the level of the manufacturing. Now, you mentioned the logs is actually a perfect example because it's the most, if you want, convoluted form. Now, the problem is that the example that and I think that you're aware because you mentioned the joints, right? The biggest problem of that project is the amount of joints, right? Because the amount of joints that you need to actually, and coordination, actually, in a way, makes the entire project redundant, because on the one hand, you're using the growth of trees to develop a structure, but on the other hand, you're like sedimenting, you're actually bringing it down to our understanding of growth by the connectors, right? Reinforcing the structure. So that's when I think it doesn't add up, because the amount of work that you need to do in relationship to the assembly, but also fabricating the pieces for them to actually breach the continuity in terms of structure, that counters is a counter argument to the same process. So we are like, you know what I mean? Like, there's a lot of very interesting directions, and I think we're not there yet. But I appreciate a lot that you're thinking about that problem, because it's like, to me, it's actually a fantastic area of investigation.
Well, thank you. Yeah, I totally appreciate that you mentioned that. Because we have to keep working with these things, right? We bought them and we have to keep working. But at the same time, I think this is kind of going to be very important to the students as well, right? So have to always kind of remind yourself, this is something you have to critically thinking, right? What's the rule? What's the rule that you work with them? what's their contribution, right? And what if you work without this robotic arm, but just using CNC milling? Is there any difference, right? So I think keep thinking that. I think it's rather important, because in the end, I think how to make complex geometries is not, it's nothing, right? So it's not go. In the end, I think there is certain level of things that we have to pursue more than the manipulations alone, right? Because otherwise, as you mentioned, the AA projects and also other projects, I see a lot of time, like although we use amazing tools, but then it's very easily to still at a certain point falling back into a very kind of linear design process, and then the tools will become only like providing complexity or optimization, or then it's going to be very sad, I have to say.
So now I would like the students to make a comment or a question, each of you. So who wants to go first?
Okay. I want to start with thanking Professor Kaicong. That was very straightforward and was very self-explanatory. And the amazing thing is how you like sort of go through the design process, and then the problems come out to you, and you like the problems embedded themselves, and you have to solve the problems. You do not expect the problems pre-designing the whole process for. So they kind of unravel themselves throughout the process of fabrication. I have a question that might be kind of redundant, because we've been hearing this a lot. But I just wanted to know your take on it. Do you think architects are going to become obsolete at one point? Like, are architects going to be non-useful? So because you in your diagram you were approaching the autonomous design, and you were saying that this is the process going to which autonomous design. Do you think at some point architects are not going to be useful anymore, are not going to be necessary?
Sorry, can you repeat the last sentence?
I'm so sorry to start here. I'm asking if you think that architects are going to be obsolete at some point, are not going to be useful anymore. So robots and
I think right.
We are engaging with deeper problems, because they are a generation that they are between 20 and 30 years old. So I want them to think in terms of the next 20 years. Well, how's going to happen to them, right? So.
That's very good. That's very exciting. Yeah, good, very good question. To me, I think what I also kind of like always keep telling my students is you have to think about like whether there are certain, for example, when we design a geometry, when we design a form, when we arrange a space, are we repeating ourselves? So that's the key, because if you are repeating yourself, of course, machine can repeat the same thing, right? I'm not like very good programmer, so I might do the kind of learning not so perfect, right? But there will be people can do that to train the model very nicely. So anything that if we repeat ourselves, it can be easily catch up by the machines. So I think, but if we don't repeat ourselves and to show our real creativity, I don't think there's any chance that there is the way of fundamentally changing whether we need designer or not. We still need designer, but it's just also the kind of like the job is changing, because traditionally we model geometries. We spend a lot of time modeling geometries, manipulating the forms, manipulating geometries, manipulating materials. But actually, those can be handled by machine. But the tricky part, what cannot be handled, is to decide what is the design space, right? Are you providing enough design freedom? Are you thinking about evaluation correctly? Are you evaluating the structural performance? Are you evaluating the energy performance? But are they really the key to let you find out, discover amazing forms? Probably not. So I think it's actually, you actually will find you need more time to think about those things. Right, it's just traditionally something that you manually do. It's just not necessary, but you will find that it's actually more demanding you have to think about what if some of your work you don't have to do it. What is the time to be spent for, right? So yeah, I think that's actually very difficult to me, and I think especially after I start to work with robotics computing, I do realize I actually more busier than before, right? So I have more jobs to do. But it's just that the jobs is not like before. I don't have to model geometries. I don't have to, kind of like figure out the structure analysis. Those can all be done by machines. But then it actually requires me a lot of new knowledge to learn and to really finally let this whole thing to create some architectural potential that we can tell that's new, right? So it's yeah. So I think in the end you will find it's more demanding, rather than utilize for us to jump into the design. Yeah.
Salma, Kavya.
Hello, can you hear me?
Yes.
Thank you so much for your presentation. It was very interesting to see how in each project you're trying to take the machine a step further and to do something that was not allowed to do. And I certainly agree with what you said in terms of how coming from a country where the craftsmanship and local know-how is very important in the assembly, as these people have through the years of experience have developed these underlying systems that would create these, that they would generate design while assembling. And I think that it's interesting how you used the machine or the robot. You gave it this chance of actually learning and developing its own knowledge.
Yes.
So not replicating what a human being can do, but taking it a step further. So that was very interesting to see. I have a question. You mentioned something in your second project, how you would make the choice for the final form in the learning process of the machine, and how you would choose meaningful forms for the machine to learn itself. And the choice is something that we had to deal with also in our studio project. We were working with machine learning and form finding. Yeah, yes. And in the form finding, at some point we chose our own forms, and that was problematic for us because we were thinking that a meaningful form for some is not for others. So that's my question. When it comes to your project, this choice, do you think that a designer has to do it at some point, or do you think that at some point the choice is going to be emergent from the teaching of the machine itself? So what do you think about this?
Yes, very good question. Thank you. Yeah, exactly. So this is the tricky part. So I can see there are two ways we can do this. One is we can say there are certain level of decision making never a machine can enter, right? Because why this form is meaningful, you need a designer. That's one way of keep working like that, right? So, but as you said, maybe one designer prefer this, but the other designer prefers something else, right? So to me, I think the reason why we found it's very difficult is because for example, when we prefer a form, except let's say the performance, there are other things we consider, right? So, and then because of those things, we think they are better. But it's kind of like something really hard to explain, right? If you think about what is a good form, right? Except the thinking of its performance, it's actually very difficult to explain clearly, right? You may consider some kind of environmental quality, right? Some kind of effects, but then they are really, difficult to explicitly define. So I think, so I think this is also a very kind of fundamental challenge for me, because so that's why I think which I didn't get chance to mention during my presentation. So my current research is actually, I work a lot on on how to consider using, let's say, artificial intelligence, artificial neural networks to help us understand those kind of criteria which we used to be considered not explainable, right? So, and I call those things, I don't have a perfect definition yet, which I think they are quite different from the performance evaluations, because performance is easy to critique, right? So you analyze the structure, it's good or bad, it's easy to use numbers to drive the decision. But then you as a designer, why you prefer this, there's a reason, of course, but the reason is very complex. It has become related with your training, right? With your knowledge, with your memory, with your preference, or even just with the deadline, right? So if you have a deadline, you make decisions very differently. So yeah, so I think it's gonna be a very challenging exercise if you really want to understand this in the studio, in a studio environment, because you have to find a method, right? And right now, I think some of the deep learning methods can actually help us, because the logic is quite simple, right? You collect a database, and then inside the database, we are sort of like build up certain common sense, saying those are good things. And you can consider, even though you don't know your criteria, you just collect probably 100 of those you prefer the form, and then there must be a pattern within that thing, right? So, and that's kind of like the general hypothesis. And then maybe the neural networks can actually kind of detecting the pattern, even though we don't know what is that, right? But I do believe that those kind of decision makings can actually a lot of time occupy most of our mind. Yeah, it's actually not the really the performance, right? How a structure is efficient or not, how material fit into each other. There is something, yeah, it's actually those cannot seem things actually more dominant. Yeah, but you definitely need a better method than, let's say, just us reading the form, right? But I do see right now you have the technology to help you, yeah. And you imagine, like, because all these machine learning, deep learning is using a lot of time the pixels, right, to compare images and such, detecting the patterns. But then 3D form is also pixel. You can imagine you can divide the form into high resolution, and then those small boxes, there's a name called voxel, right? So you can use that to actually train the network, do the same kind of detection. So there are certain research of that as well. So I think maybe that can be helpful. Yeah. But yeah, so, but I think the key is to have a dialogue with, let's say, if you finally realize a machine can make decisions, what's the difference between your decisions and the machine decision? You can keep comparing that, right? So maybe that can be also helpful. Yeah. So, but yeah, it's great that you're already thinking about this.
Thank you, Salma. Thank you, Yusuf. Kavya?
Yes, thank you for your presentation, Kaicong. I have a question regarding the technical, that is the CNN, the convolutional neural networks aspect.
Yes. Mm-hmm.
So how did you go about it? Like, did you, I mean, as an architect, we not trained, and when I read on the internet, it's totally confusing. So some parts you get, some parts you don't. So how did you actually get into it and do it so wonderfully?
I mean, I'm not really, yeah, definitely not doing wonderful, yeah, but a lot of tears. So what's happening is, because during my PhD study, and I realized I really need to know this. So I just jump into the computer science class because I really need this. So and although I spend a lot of time actually, some of the work probably for computer science students, it's just 1 week, but for me, I spent probably a month to figure out, and then got a C+ or something, But I was still happy to keep continue that, because I know I'm making progress, and I do see the goal I'm doing that is different from the computer science. Yeah, so I think I do believe there's no way we can totally rely on engineer or computer science to help us. On certain knowledge, on certain kind of like, if you really want to develop something new, you have to collect your own expertise. And I think there will be a hard kind of like really, difficult learning curve But nowadays, I think that the helpful thing is all these technologies, they're quite open source, right? So I think a couple of years ago, I still have to only learn through courses. But right now, I mean, they all publish their database online. And sometimes there are example files all around everywhere, right? So you just calm down and then start to pick one by one. Even in the beginning, it's very simple. But as long as you trust yourself to use one project maybe to really push to learn this, I think, yeah, it's actually gonna work. Yeah. So I think, but for me, my if I can say some about the lesson, it's you can't really just learn these new technologies alone. You have to use a project to drive you, because otherwise, I mean, we're all normal human. We all get lazy, right? So, but if you use a real deadline project to drive you, you will find out actually you're pretty good.
So Kaicong, you're one of the few that agree with me in terms of that, because I'm very happy that you're saying that, because that was my project at the Cooper Union. I taught for 15 years there, 14 years. And my classes were exactly about that. They were, I was against, so for instance, the typical structure in a school of architecture is you learn the technique and then you apply it. And that to me is fundamentally wrong. What I did at Cooper Union was to actually think of the project as a way to activate issues in technology. That's what the architecture information book was about. And Acadia, when we did Acadia 2010 at Cooper, a lot of people were actually, on the one hand, you have the software developers that they were agreeing with me, but the architects were not agreeing with me, right? Because they were saying, no, but it's too difficult. I said, no, that is not that it's difficult. That is the problem. If you learn something, a technology outside of the problem, you are actually dissociating knowledge. You're actually, it's a cognitive problem. You cannot do that, basically, right?
Yes.
So I'm happy because you're one of the few that actually is and maybe and my bias is that I'm inviting people to lecture that I know, that I have the suspicion that already would agree in terms of that. Because, so for instance, with Kavya asked you this question, and I'm happy that Kavya asked you this. She's going to go into computer science now. Because of the struggle that we're having internally, right? And it's exactly the answer that you gave her is the answer that I'm telling everybody, that if you don't do that, if you actually don't struggle with one, if you are expecting for somebody to resolve it from the outside or to tell you what to do, you're already out of the game in a way.
Exactly.
Like, you're already lost because that project doesn't belong to you already.
Yes.
So for instance, if you go to computer science, right, and you say, okay, teach me how to do, machine vision, right? To me, they're all totally wrong, by the way, right? Like they don't understand perspectives, they don't understand symbolic form, they don't understand systems of representation. So to me, they are all the time, and I wrote about it, and I'm writing a book about it. They are projecting conventions that, in a way, they take you back in architectural terms. They may push you forward in technology, but with very problematic biases of what machine vision is supposed to be. So I think that Kavya is going to realize that when. And I'm glad that you said about the C+ and so on, because it's hard.
It's hard.
And I did that. It's very difficult. Also, it's like talking about something completely different, because the approach is different, the mindset is different, and you're not going there to actually much to learn the technology. You're going there to actually understand the problems embedded in that technology. To me, that's what I learned from computer science. That when I realized that that actually they are actually at the deep philosophical level, they're actually trying to do the same thing that we are trying to do, which is to find different structures, basically, right? And to challenge our knowledge of what organization is. And I think at that level, that's what I'm trying to do in architecture, trying to identify what those are and how to push forward. That's why I'm glad that you said what you said. You see, we're agreeing on a lot of things, and this is not common. And I think it has to do with you going to Princeton to do a PhD in technology, which is also a weird thing. I actually, I helped initially, the movement actually to develop, I know you studied with Axel, and
Yes.
then you were with Alejandro. I was happy about that move, but also it's a place of resistance, Princeton. It's not a place where you just can do technology. So I think I can feel that you learned a lot from that tension in a way.
I know, yeah, that is the tension, yeah, and yeah, but I think at the moment I was I agree, like there are certain suffering moments. The tension, it's because in architecture school they always keep asking you what's the meaning in architecture, right? But then if you don't get this fully dirty with your hand, you can't know their potential in architecture. So you always struggle because you are still learning. But then on the other hand, you have to produce. So yeah, so it's but then nowadays when I respect, I think yeah, I really respect that kind of tension because it's a very strong driving force. Yeah, that's true. And the other thing is I would say I think I think there are certain common sense, and I think it's really we really need this because many times, for example, when I discuss something with a computer scientist, I found like in the very beginning, I mean, there are of course good people, but I think sometimes the conversation can go very wrong because they think
you're talking about something else.
Yes. Outsider, right? And they have the authority to not talking to you, right? So then it's getting more problematic but then actually, as you said, if you talk about the philosophy, we're actually thinking the same thing, right?
Yeah.
So it's just yeah. So I think sometimes yeah, but I think yeah, it's also the chance you have to meet with the people that want to share, their philosophical level common sense knowledge. Yeah, I think that communication is rather important because in the end, it's only the method is different. They are using mathematical equations, right? Computing a language, but then we are using a design language. I think, yeah, it's, but then I think in the end, we share certain goals, objectives. We actually, yeah, at the philosophical level, is the same. Yeah.
I'm very happy for this discussion. We're actually trying to, at this program, we're trying to provide the infrastructure for those things to be possible in a way, not to solidify the teaching, not to but to actually open up the problems. That's why we're teaching Python, a little bit of Python. Not obviously, you cannot compete with a computer science, but the students learn Python in order to be able to apply it by themselves to machine learning, right? And we work with open source published papers, right? And we have the students like investigate and open up and see if they can activate some of the issues that researchers are working on and apply them in relationship to a specific problem, which is the framing of the studio. So that's the methodology that we're following. And of course, they get frustrated. And I was mentioning, Kaicong, the difference. I don't know how old you are. It doesn't matter. But my generation, we didn't have that, right? So we didn't have the open source. We have to figure out everything. So we have to, and I think that the problem of the younger generations now, which is an advantage, you have more information, but already Ilya Prigogine identified that as a problem, right? Well, the more information you have available, you have to be careful because it produces the Google algorithm effect, right? That the search engine already determines your thinking, right? And then people say they call it research, when in reality you're not doing research. You're just getting the information from a structure that structure is what actually developing the research. So in that sense, to me the problem of the younger generation is that they have perhaps they start to, and it's an amazing time to be at because you have a lot of information, you have a lot of repositories that you can test directly, but the problem is that you have to be really going beyond that and understand the interesting thing about it, but not to fall into the trap that thinking that you are actually because you're able to copy paste, that you're actually doing anything meaningful with it, right? And that's to me the challenge of our program. And I am totally for collaboration, taking the work of others and expanding it. But at the same time, we have to be very careful of how we think that how much we think we are adding to the equation. And the typical problem in architecture schools is that we end up applying knowledge that is external to the discipline, and that's what we're talking about. That when you just learn something from the outside and you apply it, that's also wrong. It has to be within the subject study. So in that sense, the difficulty of our program is that it's kind of in between. It's a master program, but it's aiming at PhD level, and that's the timing is a little compressed. But we are actually trying to. I'm trying to train them so that their knowledge doesn't disappear in 5 years, right? So that's basically the objective here, that they are projected to when they're going to be working the hardest, which is to mean 10, 15, 20 years.
Well, that's that's quite amazing goal. I think this is quite important, and then I think I mean, if we really want to make some changes, I think that these kind of like challenges are quite important. So I think as you said, like to consider any project that the students are doing that can be a potentially driver for the next long term. I think that's quite important. Yes, I totally agree with this. Yeah. Mm-hmm.
All right. So thank you so much, Kaicong. We are already exhausting your time. So
no, all right.
we really appreciate it. And just hold on with me after I stop the recording. But I want to thank you for such an insightful and honest presentation. And to the students for, I can see the students, the level of the questions are pumping up. So I'm, I'm forcing them to ask a question or comment. And I think that the level is elevating each time. So thank you so much for your contribution and to your friendship to our program. And we hope to continue the collaboration as we grow. But just bear with me a little bit and we finish the presentation.
Sure. Yeah, thank you a lot for the students as well. Yeah.